Hi and welcome back. Today we'll be studying the equality of two events. So when can we say that two events which are essentially sets are equal? And this may seem like a trivial question, but in terms of probabilities and measure theory, this will actually be a quite tough question to answer. And we look at some of the caveats this question poses. Alright, so what I mean by two sets being equal is that if there is an element x that belongs to A that also belongs to B. It belongs to B as well. So this thing is valid for every element x that belongs to A, that it belongs to B as well. And similarly, every element x that belongs to B will belong to A as well. So these two conditions, when they are satisfied, is what we mean by A equal to B. Now, how do we express it in terms of probabilities? Now, to do that, can we just say that probability of A and B are equal? So let's just get done with that. Technically, no, that's not possible. So consider this sort of situation where, consider this sort of situation where this is A, this is B, and now A and B, they don't have any common elements. But suppose we design a probability measure over this such that the probability of A and B is equal, but they don't have the same elements, but their probabilities are still equal. This sort of thing is possible, and hence we cannot just end it at this, that probability of A is equal to probability of B. The day is over, we are done, let's go. No, we cannot say that. No, the day is not over. So that's why I want you to look at this diagram. So this is A, B, this is the overlap region. This over here is the set of elements that belong to A but are not there in B. This over here is the set of elements that belong to B but are not there in A. So I denote them by A B bar and A bar B respectively. And obviously the overlap region is called AB. Alright. Now think for a moment. If there is no element in AB bar and there is no element in A bar B, so that means these two events are null sets, okay, then that would mean that each and every element of A and B will fall in the overlapping region only. And so that's why we can say that if the symmetric difference, that is the union of AB bar and A bar B, if the probability of that is 0, I'll come to this. This is where the caveats start, by the way, but like, bear with me till here. Suppose the symmetric difference, that is AB bar union A bar B, the probability of this thing is 0, then that would mean that we can split this into two separate terms, that is AB bar and A bar B. We can split them into the probabilities of those. Why? Because these two are mutually exclusive and they union up to the symmetric difference, and so splitting that into two probabilities, the sum of that is 0. But according to our axioms, the probability measure is always greater than or equal to 0. So that would mean individual terms AB bar and A bar B, their probabilities will also be 0. Now look at this. We can write A as a union of AB bar and AB, right? And hence P of A is the same as P of AB. Similarly, P of B is also the same as P of AB, because we can write B as a union of AB and A bar B. So in this case, we have just found that P of A is the same as P of B, and that is the same as P of AB. Okay, so there you go. This is our condition, and this actually works, and it's intuitive. Why? Because all I'm saying is that these two regions, which contain disjoint elements and not the overlapping elements, those two are, well, null sets. They don't have anything. And so how have I encoded that information? I have encoded that information by saying that P of AB bar union A bar B, that is the probability of these two things put together, has to be 0. Well, that sounds fair. If these two add up to null sets, then yeah, sure. I mean, if these two contain nothing, why not? Let's go. The probability of AB bar union A bar B is 0. But wait, that's where this caveat starts. I'll tell you why. Now, does this P of, this is how I denote the symmetric difference, by the way. So whenever I write A triangle B, that means AB bar union A bar B. Okay. So in this case, P of A triangle B, that is symmetric difference, the probability of the symmetric difference is 0. But does that mean that the symmetric difference is exactly 5? That is the what do we say, impossible event. Does that mean that this thing is the impossible event? I mean, I inherently assumed that when proving that thing and giving you this condition. Does this really mean that the symmetric difference is the impossible event? Well, technically no. That's where I'm going to give you an example. There can exist events A such that P of A equals 0. They are called zero measure events or zero probability events. And yeah, they are impossible. But yeah, they are not equal to 5. I mean, they do A does contain some element inside it, just that the probability of that element we have assigned it as 0. It's not exactly the empty set. Okay. And so with that, suppose I have a coin which can give me heads and tails, but technically a coin can also land on its sides, just that the probability of that is very small. It's 0 for all practical purposes, and so my sample space will basically heads, tails and sides. Now the probability of heads is P, probability of tails is 1 minus P, probability of side is 0. That's how I assign my probabilities. This over here is a set of 0 measure or 0 probability in this case. And notice what happens here. If I take the event A1 as just heads, my event A2 is heads and sides, then P of A1 and P of A2 is P. The probability of A1 intersection A2, which is H, the probability of A1 intersection A2 is P. And so A1, A2, the probability of A1, probability of A2, probability of A1, A2, all of them are same. But A1 is not equal to A2. This happens because I have this event of 0 probability. I just blasted this condition in the face. I mean, why is this happening? So the condition this thing over here, the probability of symmetric difference being 0, it does imply A equals B, but only up to sets of 0 measure. Yeah, so this is actually a term. It means that if I don't have any set of 0 measure like this, if I don't have any 0 measure events, then that would mean A will 100% be equal to B. If I just don't have these sort of things, non-empty sets with 0 measure, if those sort of things are not there, then A will be equal to B, but otherwise A will almost be equal to B. So, or A will be equal to B up to sets of 0 measure. That's a term, guys, please memorize it. So in measure theory, any set n such that the probability measure of n is 0, that thing is called a null set. So over a class of sets or events which we call F, many null events besides the impossible empty set impossible event, that sort of stuff may exist, as I illustrated in the previous example. So if we have that n1, n2, n3, many of them, with the probability of those being 0, all of them are null events. And so in this P of A equals P of B equals P of AB, it will surely give me A equal to B, but that's only if such events do not exist in the first place. If these zero measure elements are not existing, then we are totally fine. We can easily say that A equals B. So that's what I mean by up to sets of zero probability. So ignoring these null events, A is equal to B. So that was the caveat I wanted to introduce while exploring the equality of events in terms of the probabilities. And I hope you understand this much. In the next lecture, we'll be delving into something else. Alright, with that, thank you, goodbye, stay tuned for the next one.